Hello everyone. So today in lecture 13 we will try to get the probabilistic interpretation of wave function. So during our last lecture we understood that from the time dependent Schrodinger equation we can represent the wave function psi as a function of both position and time. So in general, psi xt can be represented like this, which is the exponential function in terms of time t, and psi x. So this psi x is actually represents the amplitude of the wave psi xt. So in other words, this is called the amplitude function. So now classically, that means according to the classical physics, the intensity, all right, the intensity of any wave is proportional to the amplitude square. Okay, it is proportional to the amplitude square. So now here in quantum mechanics we will try to see that how far the intensity term holds true. So in quantum mechanics, instead of intensity we have a term called probability. So this term represents the probability of finding, or that means the chance of finding a particle in a certain space, in a certain finite limit. So this probability of finding a particle is actually similarly very similar to this above consideration, is proportional to the amplitude square. Okay, so what is the amplitude here? The amplitude function. So amplitude means basically the amplitude function. Amplitude function is psi x. Okay, so we can write definitely the probability. In short, I'm writing PR proportional to psi x. All right, so psi x, something like this, psi x square. Okay, so now let's see what is the significance of psi x square of this quantity. Now we have two possibilities regarding considering psi x. So that means psi x can be either real or psi x can be imaginary as well. Okay, so let's see how it term can be explicitly written. Okay, so considering psi x as real and psi x as imaginary, so considering both the possibilities we will try to find an expression that covers the both. So let's clear the board and write it freshly over again. So therefore we represent the intensity of a particle, which is equivalent to the probability, that can be proportional with psi x square. So the psi x whole square can be psi x star psi x if psi x is imaginary. So this means that it is the product of the conjugate of the complex quantity with the complex value. All right, so which can be nothing but the product of the absolute value, means the square of the absolute value. So this is the definition of the probabilistic interpretation of psi x. So originally, if we take a look, that if we take the square of the absolute values of psi xt that was obtained from the Schrodinger's time dependent equation. So the solution to that equation, which is the time dependent wave function, so the square of the absolute value we can write as something like this. Okay, because we know that psi xt is a complex number, so therefore we can easily write e to the power minus I e t divided by h cross, and that would be the complex conjugate multiplied by psi x. Okay, again complex conjugate whole multiplied by, once again, e to the power minus iet divided by h cross multiplied by psi x. All right. So what we get now? So the complex conjugate of e to the power minus something, that becomes e to the power I star t divided by h cross. All right, this again multiplied by e to the power minus iet divided by h cross. All right, multiplied by psi star x psi x. All right. So now the question is, what is the value of this one, e to the power I something multiplied by e to the power minus I something? So definitely this comes to e to the power 0, means unity. Okay, so this becomes e to the power 0 psi star x psi x. All right, and we know that e to the power 0 is equal to 1, provided, so we can directly write this into this, provided we are assuming that E is a real quantity and E star is equal to E, and this only happens when E becomes real. All right, so in fact energy is a real quantity, so we can safely write that this is equal to e to the power 0 1. So whatever we get is basically psi star x psi x. So, and what is this? So this becomes nothing but psi x. All right, so we can actually come to the definition of this. Okay, so one interesting, very interesting thought is that the time dependent quantity psi xt, and we take the square of its absolute value, which becomes equal to, means identical with a time independent quantity psi x, and the or it's the square of its absolute value. So you see, when we square up a time dependent Schrodinger wave equation, means wave function, sorry, psi xt, it becomes identical with psi x square. So this is independent of time, so we can write that this is independent of time. So in other words, this quantity, okay, so now we can officially call it this psi xt square or psi x square. This is officially called, in more scientifically accurate term, it is called the probability density. So far we have been colloquially referring to it as a probability, but scientifically the more accurate term is the probability density. So the density term is a very important point. So what we found, that even though we can take a wave function for a time dependent system, the same wave function, when we consider its probability density becomes independent of time. So therefore we can quickly write, by erasing this part, that okay, so once again psi x square of the absolute value, so this is probability density, okay, is independent of time, or in other words, the probability density represents a stationary state. So probability density is stationary, means it doesn't depend on time, and because of this particular property, psi x, okay, is called the stationary state wave function, or stationary state, simply stationary state function. But remember, this doesn't mean that the particle is stationary. So with a caution I write, it doesn't mean that the particle, because this is a common misconception some people have, that stationary state wave function means the corresponding particle is stationary. So no, answer, it doesn't mean that when psi x represents a stationary state wave function, it doesn't mean the particle is stationary. The particle can be moving, can be stationary, anything, but still uh, it represents a stationary state wave function. Why? Because the square of its absolute value represents a time independent quantity, which is the probability density. Okay, so next we discuss few more things about the probability rather than the probability density, and let's see what is the very small and fine difference between probability density and probability. So let's find it out. So before we define the difference between probability and probability density, let's first take a look that when initially Schrodinger developed quantum mechanics, so he considered quantity called electron charge density, probably to represent the electron's positions or chance of finding it between x and dx. So he represented the quantity by multiplying the charge of the electron. Here E represents the charge of the electron multiplied by psi star x psi x dx. But later it was found out that such kind of consideration gave some realistic problems, and this was not accurate. So even great men like Schrodinger's, they even made mistakes. So but later it was correctly interpreted by Born. Okay, so the Born's interpretation is basically nothing but the probability. So let me correct that. uh, so Born interpreted as the probability of finding an electron between x and x plus dx is equal to psi star x psi x dx. All right, so according to Born, till now this has been the most accurate representation of finding a particle or finding an electron between x and x plus dx. So now we come to the question probability. So of course now we knew that this part is called the density, so we can call it the probability density. So the probability of finding the particle over a finite space, so probability of finding a particle between between 2 points, right, like A and B, such that A less than equal to x and x is less than equal to B. So we can represent this thing, the probability of finding the particle between A and B is equal to, we can write that psi star x psi x dx, and we have to integrate that probability density with respect to dx within A to B. So this definition, all right, so whatever we have written here, so this becomes the probability of finding a particle within a finite space or finite volume. If it is one dimension, then we call it a space. If it is a three dimension, we call it a volume. And of course, dx would be replaced by the volume element dv. Okay, so now we understand the difference between the probability density and probability. So probability is the total integral over a finite limit, and the probability density is just this function, which is psi star x psi x. All right, so now we come to another point, that is called the normalization of a wave function, which is based on the total probability of finding a particle. All right, so let's delete this part and let's discuss this. So one of the most important factors is the total probability. Okay, so the total probability should be always is equal to 1. It cannot be more than 1. So now the thing is, suppose a free particle, okay, moving in a direction x, okay, so the question is, it can move from minus infinity to plus infinity anywhere. So what is the total probability? So definitely the particle is present anywhere between minus infinity to plus infinity. So the probability of finding the particle within minus infinity to plus infinity is 100% and is therefore 1. So how can I represent the total probability of finding the particle between minus infinity to plus infinity? So it is definitely like that. So the probability of finding the particle between minus infinity to plus infinity is equal to, the same way we assume that the psi star x becomes the wave function of the particle. So we have to integrate between minus infinity to plus infinity. All right, and we know that value should always be equal to 1. All right, so therefore if we can okay, so before that, so this is a condition. All right, so in other words, if we change this minus infinity to plus infinity to some finite limit, say for example minus infinity is a and plus infinity is b, so therefore suppose the particle is confined within limit a and b, okay, it's confined means we have 100% chance to find the particle between a and b. So how we can represent the probability? So that probability of finding the particle between A and B, all right, should be represented as A, B, psi star x, psi x dx. All right. Now the thing is, theoretically this value should be 1, all right, but practically it should only be 1 if and only if psi x fulfills a special criterion. What is that criterion? That psi x, so this should be 1 provided, I can write, provided psi x is normalized. So what is normalized or normalization function, normalization process? It is just the reverse. So we take the value of psi in such a manner that if we multiply it with complex conjugate, and if we apply the corresponding limits depends on the system, whether it is minus infinity to plus infinity, 0 to a or a to b, it should be equal to 1 because the probability should always be 100% within the limits. So if psi x fulfills that criteria, that multiplying it with by complex conjugate and integrating within a certain limit becomes unity, then only we call that psi x is normalized, or we have a normalized wave function. So now let's take a look at the situation of free particle in a one-dimensional box. So what happened to that case? All right, so let's quickly erase this part and finish our discussion. So here now we will discuss the normalization of a wave function according to the Born. So according to the Born interpretation. So how Born interpreted is this way, that okay, let's take an example of a free particle in a one-dimensional box. So what was the wave function that we have found so far? that we have found psi x, okay, is equal to b sine n pi x by a. All right, where n is equal to 1, 2, 3, etc. Remember, we could not solve for b, or we could not find an exact specific solution for b because there was no condition to define b. Okay, so now what could be the b? According to the Born interpretation, the b should be the normalization factor or the normalizing constant. So how to find b? So therefore we have to consider this thing that since in the free particle within a one-dimensional box, it is confined within x is equal to 0 to x is equal to a. So the probability of finding the particle anywhere between 0 to a is always 100%. Therefore we have to apply this condition. So therefore we write that the probability of finding the particle between 0 to a, okay, should be equal to 0 to a integral psi star x psi x dx. All right, and this should be equal to 1. Okay, and this is called the Born interpretation of the normalization. So therefore we have to solve from this equation, we have to solve for any unknown constant of psi x, and that would become our normalization constant. Or we can write here, because psi x is b sine n pi x by a, so therefore we can write 0 to a. All right, we have b star sine star n pi x by a multiplied by b sine n pi x by a dx is equal to 1. All right, or so this is constant, this is constant, we can take it out. We can write b star b 0 to a, and since sine n pi x and sine n pi x, these are all real, we can write sine square n pi x by a dx is equal to 1. And so b star b, or we can represent this as the square of the absolute value 0 to a sine square n pi x by a is equal to 1. All right, so now we get an equation here. So from this equation we need to solve the value for b. So how do we solve it? So let's quickly take a look. Okay, so therefore we already got this equation, or to solve we can directly write b is equal to 1 divided by root over of this integral 0 to a sine square n pi x by a dx. Okay, so forgive me if I have missed the value dx in earlier part also. So here we have to find the value of this integral. Okay, so can you find this value of this, and for the whatever the final value of b? This is your job to verify that solving this integral you get a value of b as root over of 2 divided by a. A is the dimension, that means the length of the one-dimensional box. So please try yourself how to find this integral. Okay, that's your job. So therefore, since we get the value of b is equal to root over of 2 by a, our normalized wave function psi nx for a free particle in one-dimensional box becomes root over of 2 by a sine n pi x by a. So where we have these conditions, n is equal to 1, 2, 3, 4, positive integral, etc., and our limit 0 this. So x varies between 0 to a. All right, so this becomes the complete wave function for a free particle confined within one-dimensional box. All right. So now probably we have understood the process. So how we calculated the value of B, and the value of B is called the normalization constant. And this is the process how we normalize a wave function. Okay, just by squaring it up and equating with respect to unity. So before we finish today's lecture, I have one small question for you. Probably if you have understood today's lecture, then probably you will be able to solve this question. So the question is, find the probability. So this is a particle confined in a one-dimensional box. Okay, so find the probability of of a particle within 0 x a by 2. All right, so this is the factor. So that means finding the probability within the first half of that box. So find the particle between 0 to a by 2. So x is greater than equal to 0 and less than equal to a by 2. Okay, so that means find the probability within this much location. Okay, so I guess if you follow today's lecture, you will be able to solve this problem. All right, so in the next lecture we will have some more statistical interpretation on very basic quantities of quantum mechanics. Okay, so till then, goodbye, and we'll see you in the next lecture. All right.